Well, hello everybody. Today we are going to talk about Chapter 8, which are one-way ANOVAs. So that's what we'll be discussing today. ANOVA stands for Analysis of Variance. ANOVA, Analysis of Variance. And we're doing one-way analysis of variance in this class, although there are more complex versions of ANOVA that you may learn if you go on to take further types of statistics. But in terms of one-way ANOVAs, up until this point in class, we've looked at an independent variable that has two levels or two conditions or two groups. So we want to compare, males and females on their math reading abilities, or we want to compare people who take some kind of medicine compared to people who don't take the medicine on symptoms of anxiety, or something like that, where we're comparing two groups. But very often we're interested in comparing more than two levels or more than two groups on a specific variable. Two is pretty simple, but more than two lets you kind of gives you more information about what you're looking at. So if you're doing ANOVA, you still have one independent variable, one treatment variable, and one dependent variable, right? That's the outcome variable. But your independent variable has more than two levels. So if we are looking at the independent variable of hours of sleep, and we have a 0 hours of sleep group, a 4 hours of sleep group, and an 8 hours of sleep group, and we compare them all on test score, thinking that somehow hours of sleep would impact test score, and for an ANOVA we would have 3 or more groups, so 0 hours of sleep, 4 hours of sleep, 6 and 8 hours of sleep. Or if we're interested in what kind of therapy or treatment is most effective on symptoms of depression, we could use the levels of one group taking medication, one group doing therapy, and one group doing relaxation training, and then looking at symptoms of depression. So if you have one independent variable, but you have 3 or more levels of that variable, and still only one dependent variable, you're doing an ANOVA. So if your DV is measured on an interval ratio scale, meaning it's a number scale, and your IV has 3 or more levels, ANOVA is appropriate. So the question is, why do ANOVA, and why not just do multiple t-tests? We already know how to do a t-test, so why don't we just do a bunch of comparisons between the two groups? And the problem with that, why we can't do multiple t-tests, is that that will increase our type 1 error rate. Remember, type 1 errors are false alarms. False alarms or type 1 errors, that's when you reject the null hypothesis, so you're saying that your independent variable has an effect, when in fact it doesn't. And we set our type 1 error rate at our alpha level. When I say test this data at an alpha of 0.05, that means that you're using a 5% type 1 error rate. We don't want there to be any more than 5% type 1 errors, and so we actually can set that rate by saying test this at the 0.05 level. So if you were to do something like our study on hours of sleep and test score, and we have 3 groups, 0 hours of sleep, 4 hours of sleep group, and then the 8 hours of sleep group, and after that we give them all the same test at the end and compare their test scores. We could do a bunch of t-tests. We could do a t-test and compare an independent samples t, the 0 hours of sleep group compared to the 4 hours of sleep group, and then we could compare the 0 hours of sleep group to the 8 hours of sleep group, and then we could compare the 4 hours of sleep group to the 8 hours of sleep group. And by doing these 3 comparisons, we've compared each of the possible combinations from those 3 groups. But the problem is that each time we do a t-test, we have a type 1 error rate of 0.05. There's a 5% chance of making a type 1 error for the first comparison. there's a 5% chance of making a type 1 error for the second comparison, and a 5% chance of making a type 1 error on the third comparison. And so what we say is if you were to do it like this, if you were to test all of these different possible combinations, you inflate or you increase your type 1 error rate. This chart you don't have to at all memorize, but just to show you, if you have two means, right, you would be a t-test, you're comparing two groups. There's only one comparison you can do there, and your type 1 error rate is that 5%. But if you did the individual t-tests for three means, like the 0 hours of sleep, 4 hours of sleep, and 8 hours of sleep group, now you've got three possible comparisons, which I showed you here. And now your type 1 error rate is almost at 15%. There's a 15% that somewhere in those three comparisons you will have made a type 1 error. When you have four means, now you've got 6 comparisons and almost a 27% chance that somewhere in all of those individual t-tests you would have made a type 1 error. And you can see by the time you get to 7 groups, like if we said we're going to compare people who have 1 hour of sleep, 2 hours of sleep, 3 hours of sleep, 4 hours of sleep, 5 hours of sleep, 6 hours, and 7 hours. So we have 7 groups on test score. There's now 21 pairwise comparisons, 21 pairs of means that can be compared. And if you do that, you are at a 66% chance that somewhere in there you've made a false alarm. So as the number of your sample means increase, the probability of making a type 1 error increases. And we don't want errors. We do not want there to be a false alarm in our data set. We want to cap that rate at 5%. How do we do that? Well, instead of doing multiple t-tests, we do ANOVA. ANOVA lets us look at all of those means in one statistical test. And so since we're only doing one test, we can do that at the alpha level of 0.05 and keep our 5% type 1 error rate. So let's look at an example. Supposing we're interested in looking at test scores, right, after 0 hours of sleep, 4 hours of sleep, or 8 hours of sleep. And we're measuring test scores, which are on a ratio scale, a number scale. Our research question is whether hours of sleep affects test score. Okay? And we would do an ANOVA because we have 3 groups. If we only had 2 groups, if we were comparing only people who slept 0 hours and people who slept 8 hours, well then we'd be doing a t-test. But because we have 3 groups, we're doing ANOVA. The logic of ANOVA is that our null hypothesis, again, is that our independent variable has no effect, and that all of the groups that we compare should have the same mean. So the independent variable would be something like the hours of sleep, which is our independent variable, has no effect on test score. And so that after 0 hours of sleep, or 4 hours of sleep, or 8 hours of sleep, participants will have the same average test score. There's no effect of hours of sleep on test score. That's our null hypothesis. The alternative hypothesis is that hours of sleep does impact scores on the test, and that test scores will be different somewhere among these 3 populations. All right, so let's take a look at this picture. We're going to keep coming back to it for a little bit to just try to help you understand some of the terms in ANOVA. We have what we call between group variability and within group variability. And in this case, here we've got some frequency distributions. Let's say this x-axis is test score, and here is frequency. And these are our 3 groups. 0 hours of sleep, that'll be our blue group, right, with their mean right here, and they performed lowest. This pink distribution, that would be our 4 hours of sleep group. They performed somewhere in the middle. And the green distribution, this would be our 8 hours of sleep group. There's their mean score, and they got the highest score. All right, and you know that these, like this pink distribution continues behind the green one. It's just that they're overlapping. and this blue distribution continues behind the pink one. It's just that they're overlapping. So we've got 3 groups that we're comparing, each with their own mean. Okay, let's start with the idea of between group variance or between group variability. This suggests that each sample has its own mean, and if we have 3 samples, we'll have 3 means, right? We'll have the mean test score for the 8 hours of sleep group, which in this case is right here. We'll have the mean test score for the 4 hours of sleep group, which in this case is right here. And the mean test score for the 0 hours of sleep group, which is right here. If the null hypothesis is true, each sample mean should be the same, right? We'd say there's no difference in test scores between the 0 hours of sleep group and the 4 hours of sleep group and the 8 hours of sleep group. And so the idea of between group variability is really what it says. It's the difference between the group means. How much difference is there between the means? Now, if you could imagine that I could slide these distributions along this axis here where it says score, the x-axis, and imagine I take this green distribution, this is the 8 hours of sleep group, and pull it as far as I can over here to the right, suggesting that these people got a very high score. They're over here. Everybody got, their average score is a 95. And imagine I take this blue distribution, which is the 0 hours of sleep group, and pull it as far as I can to the left, suggesting that everybody in this group got a low score, right? Their average score was 10%. And this pink distribution stays right in the middle. The farther I pull these distributions apart, so if we have a mean over here very far to the left, very high mean, we've got some mean right in the middle for the 4 hours of sleep group, and we have a very low mean over here for the 0 hours of sleep group. We have a lot of what we would call between group variability. There's a lot of difference between the means. The between group variability represents our treatment effect. If we have a big effect of, in this case, hours of sleep impacting test scores, well then we should have a lot of between group variability. The difference between the means should be very large, suggesting, right, that this people who got 8 hours of sleep had a very high, typically a very high test score because they did very well. People who got 0 hours of sleep had a very low test score because they tend to not to do very well. And people who got 4 hours of sleep were somewhere in the middle. As the distributions and the means get closer and closer together, so now if you could imagine I'm sliding this green distribution closer and closer to this pink one, and then I can also slide this blue distribution to the right, closer and closer to the pink one. Imagine what would happen if all 3 distributions lined up completely and each of them had the same mean. In that case, what would be the between group variability? How much difference would there be between the means if they all had the same mean? Well, there'd be 0, right? There's no difference between the means because all 3 of those distributions are lined up right on top of each other and there's no variability between the means. And that would suggest we have no effect of our treatment, right? It doesn't matter if you got 8 hours of sleep or 4 hours of sleep or 0 hours of sleep. Everybody got the same mean score. That would suggest there's no effect of our independent variable. That's kind of what we would imagine under the null hypothesis. No effect. And the more spread out these distributions get, the more between group variability there is, and that's telling us something that there is more and more of an effect of our independent variable. So like I said, each sample has a mean, and if we have 3 samples, we have 3 means. If the null hypothesis is true, each sample mean should almost be identical, maybe slightly different because there's some sampling error, but they should pretty much be identical. So the between group variability under the null hypothesis is 0. There's no difference between the means under the null. When the null is not true, when our independent variable does have an effect, then we're saying that the populations have different means. And the variability between the means, the fact that some groups have low means and some groups have high means, that's what we call the treatment effect. It causes the means to spread out. Okay, so this is the between group variability, and you can see this picture is depicting the difference between the means of these three distributions. That is between group variability. Variability between the means. But we have one more type of variability that we need to talk about, and that is what we call within group variability. Within group variability has to do with our error variability, and this is talking about the variability within a specific group. So let's just look at this green distribution here, which represents people who slept 8 hours. What this is showing us is that this distribution has a mean. Let's say there were 50 people in this 8 hours of sleep group. Well, here's the mean, but everybody in this 8 hours of sleep group didn't receive the same score, right? If I had all of you who are in my class and asked you all to sleep 8 hours the night before a test and then give you all the same test, you all won't get the same score, right? There'd be some variability. We call that within group variability. Within group variability represents all the participant variables, all the participant things that make people score differently. So what would make some people score higher on a test and some people score lower on a test? Well, anything from how much they studied, how motivated they are, how much they like the class, how smart they are, do they have a quiet place to study or not, what they ate for breakfast, if they're feeling sick that day. All of those variables go into this within group variability. So some people score really high on the test. These are people who studied hard, maybe, and are smart and really like the class and are feeling great that day and had a good breakfast and are ready to take the test. And then we've got some people who score lower, and maybe these are people who, oops, they forgot to study and they're not feeling great, they're feeling kind of tired, and their roommate was really loud the night before, so they just couldn't really get a good night's sleep or concentrate on studying. All of that goes into this within group variability. There's only one thing that does not account for within group variability. Can you think of what the one thing is that does not account for within group variability? The one thing that doesn't is your independent variable. That's, in this case, hours of sleep, because remember, in this green distribution, everybody in here has slept 8 hours. We've held that constant. So that is not an explanation of why some people scored higher or lower. But anything else you could think of that could affect test scores would go into within group variability. So the question is, why do people have different scores? All these participant variables, intelligence, motivation, anything you can think of that would cause people to get a different score on a test other than the independent variable. Because remember, everybody in the group, within the group, are the same on that independent variable. Because then we could look at within group variability for the 4 hours of sleep group. Again, we would think of all the participant variables that could explain their performance. The one thing that you can't say affected their performance was hours of sleep, because everybody in this pink group slept 4 hours that night. So you can think of within-group variance as the variance due to unknown or chance factors. We also call it error variance. Anything that causes people to have different scores, and it's kind of all the stuff we don't want to study, and that's why we call it error variance. All right, so the logic of ANOVA is that we compare between groups variability and within groups variability. And when you use the formulas to compute ANOVA, when the null hypothesis is true, meaning there's no effect of the independent variable on the dependent variable, the ratio of between groups to within groups variance, they're the same, and so the estimate is 1. So if the between groups estimate of variance is 100.5, and the within groups estimate is 100.5. In that case, those two are the same. We know that the null hypothesis is true here, that there's no effect of the independent variable and the dependent variable. If you do this as a ratio between groups over within groups, you get 1. When the null hypothesis is true, your ratio of between groups variability to within groups variability is 1. Okay, and I just made these numbers up, the 100.5, it could be anything. I'm just making them up, but they would be the same under the null. 1 is your ratio. However, when the null hypothesis is not true, the between group variability, the difference between the means, should be larger than the within groups variability. So if the between groups variability is 454.3 and within groups is 100.5, then when you do the ratio, 454.3 divided by 100.5, you get 4.5. This number is greater than 1, and that's starting to suggest that we do have an effect of the independent variable on the dependent variable. Okay, so when the null is not true, meaning when the independent variable does have an effect, if we think hours of sleep does impact test score, the between group variability between the means, should be bigger than the within groups variability. So which brings us to the rule here for ANOVA. When the null hypothesis is true, the ratio of between groups variability to within groups should be about 1. And if the alternative or research hypothesis is true, the ratio of between groups variability to within groups should be greater than 1. And that brings us to the F ratio. So at this point, we've learned a lot of letters, right? We started with a Z-score, a T-score, and now we're at an F. An F ratio is for ANOVA, and the formula there is between groups variability over within groups variability. This is something you just have to remember. Again, SPSS will do this for you, but just to understand the concept, between over within. I think about it, I remember it, that it's alphabetical, right? B and then W, between, over, within. And that's how we get the F ratio that lets us know whether or not our results are statistically significant. So the F ratio is this key to ANOVA, between, over, within. Don't restart my computer, that wouldn't help us at all right now. So like I said, between, over, within in alphabetical order, larger between group variability, smaller within group variability. That means you're going to have a greater likelihood of a significant ANOVA. When you have small between group variability and large within group variability, you have less likelihood of a significant ANOVA or F ratio. So we're going to go through a few examples here to try to help you understand the idea of between and within group variability. So in this case, we're looking at the independent variable of school. We've got 3 schools, School A, School B, and School C. all the students are in first grade, and we want to know if the school that they attend, that a student attends, impacts their math grade. These are math scores on some kind of standardized math test. Okay, so in school A, I have 3 participants, and they got a 16, a 14, and a 12 on the math test. School B, again, I have 3 participants, a 20, a 16, and a 13. And school C, I have 3 participants, 10, 19, 17. Typically, you would have many more students in each group, but I wanted to keep this small so you could kind of see what's happening. You don't have to do any of the calculations. SPSS will do this for you, but you will find that school A, their mean math score was a 14. For school B, their mean math score was a 16.33. And for school C, the mean math score was 15.33. So when we look at the idea of between group variability, how much difference do you see between the means, between the mean of 14 and 16.33 and 15.33? Does this look like a lot of between group variability or not very much? Not very much, right? It's going from a 14 to at the highest a 16.33. That's like a 2-point difference. If you were a parent, would you be like, I must have my child go to school B because they're going to do so much better in math compared to school C? I'm not seeing that, right? This is a pretty small amount of between group variability, especially when you compare it to the within group variability. That's the difference in scores within a group. So for school C, the difference is between a 10 and a 19. That's a 9-point difference. It's a lot more variability than between the means where we had 2.33 points of variability. How about a 13 as the low in school B to a 20? Well, that's a 7-point difference. Again, that's a lot more than the between groups. And here we've got about a 4-point difference. Even so, it's greater than the between group variability. So in this case, we've got very little between group variability, but we have a lot of within group variability. So what are we thinking here? Are we going to find a significant effect of school on test score? Well, hopefully you're going to think not, but let's go through it. So step 1, as always, we state our hypotheses. The null hypothesis is that mu1 is equal to mu2 is equal to mu3, right? And this could also say the mu for school A is equal to the mu for school B is equal to the mu for school C. That all 3 means should be about the same. That's the null hypothesis. The alternative hypothesis you write just like this, that the null is not true. This one a little bit different than how we typically write our null hypotheses. Why don't we write mu1 is not equal to mu2, which is not equal to mu3? Well, if you did that, what you're saying is every single mean has to be different from each other. And to get a significant ANOVA, that's not the case. We don't need every single school to be different from each other. It could be that school A got a mean of 14, school B got a mean of 14, let's assume. But school C, their average score was 40, much, much higher. So in that case, we would still have a significant ANOVA. There would be no difference if you went to school A or school B. Everybody sort of got the same score. But there's a big effect of going to school C. So for our hypotheses, our alternative, all we're saying is that this is not true. The null is not true, and that somewhere in there, at least one mean is different from at least one other mean. That's all we're saying. For you to get a significant ANOVA, at least one of the means has to be different from at least one other mean. So this is the way you write your hypotheses for ANOVA always, and just those are ones you have to remember. We run our statistics in SPSS. We'll get our descriptives, which are here. So school A, there are 3 people. You saw that. And the mean was 14, and here's the standard deviation. For school B, again, we had 3 people. There's the mean of 16.33 standard deviation. School C also had 3 people with a mean of 15.33 in the standard deviation. And here's our results from ANOVA. Remember I said we have between group variability and within group variability. You need to have your degrees of freedom. Now that we have these 2 estimates, we actually have 2 separate degrees of freedom. So between groups variability, the between groups degrees of freedom is 2. The within groups degrees of freedom is 6. Mean square, this is our measure of variability. So between groups variability of 4.11, within 12.88. Here's our F ratio of 0.31. Remember that we said if it was around 1, that's not statistically significant. This is even less than 1. And here's our significance. If we test this at the 0.05 level, then this sig has to be less than 0.05, which in this case it's not. It's much greater than 0.05. So we make our conclusions. Our statistical conclusion is that we fail to reject the null, or you could say accept the null, because our obtained P of 0.74 is greater than the critical P of 0.05. Same thing as we've done in ANOVA, in t-test. We compare this significance value to our test value of 0.05. And if it's greater, then we fail to reject or accept the null. And what we say here is there is no evidence to suggest that school A, school B, or school C affects math test score. And this is the way you have to write out your results. An F with 2 and 6 degrees of freedom. Between, within. You always start with between and then within, same alphabetical order, equals 0.32. And there was our F of 0.32. P is greater than 0.05. Okay, let's think through another example. In this case, we're now comparing math scores all in one school, but we're comparing grades. We've got 3 first graders, 3 fifth graders, and 3 12th graders. Okay, and they're all taking the same math test. So, as you might imagine, the first grader's mean score is only a 14. The fifth grader's mean score is a 54. The 12th grader's mean score is a 92. And we're looking at the question of, does grade in school affect math test score? What does it look like to you? How is our between group variability? Is it small or large? It's pretty large, right? We're going from a 14 to a 54 to a 92. And if you compare that to the within group variability, right, from an 89 to a 96, that's what, a 7-point difference. A 51 to a 58, about an 8-point difference. There's a 4-point difference. But from here, the first grade mean to the 12th grade mean, that's like an 80-point difference. All right? So we've got a lot of between group variability compared to a smaller amount of within group variability. Do you think we're going to find a significant ANOVA here? Does grade in school affect math test? Well, I think so, but let's look at it. Okay, here's the null hypothesis, or the hypotheses. Same as before, the null is that the mu for group 1 is equal to mu for group 2 is equal to mu for group 3, that there should be no difference in math test score based on grade in school. The alternative is that the null is not true, that somewhere in there we're going to find a statistically significant difference. At least one mean is different from at least one other mean. We run our test in SPSS. Here are 3 people in each group. First graders have a mean of 14, fifth graders a mean of 54, 12th graders a mean of 92. And we run the ANOVA. Again, we have the same degrees of freedom, 2 and 6. Here's our between groups variability estimate, 4,564. That's huge. Yeah, that would look almost like your teacher made up the data, which I did. The within groups variability is 12. We divide between over within, or SPSS does it for you, and you have an F ratio of 380.33. So if this value is close to 1, the null hypothesis is true. If the farther away it is from 1, the more likely you will be to reject the null. In this case, here's our significance value of 0.000. We're comparing this to our alpha of 0.05, and 0.00 is less than 0.05. So, our conclusions. Statistical conclusion, we will reject the null because our obtained P of less than 0.001 is less than the critical P of 0.05. Please remember, if you get a significance value in SPSS of 0.000, remember this is your chance of making a type 1 error. This never is 0. Even if it's at 0.00 here, that would literally suggest that there's no chance you've made a type 1 error. There's no chance you've made a false alarm. Now, how can you be sure that you haven't made a false alarm? How can you ever be 100% sure that your results are accurate? Well, the only way would be to test the entire population, not to just use a sample to estimate about the population. And we've used a very small sample here of 9 first graders, 5th graders, and 12th graders. We certainly could be making an error. What's happening here with SPSS is that this is a very, very small number, and SPSS is just rounding to 3 decimal places. So this might be 0.000000008, and it's just rounding to the 3 decimal places of 0.00. What's important for you is that in our convention of how you write this in your results is that you just say P is less than 0.001. You never write P equals 0, because when you say P equals 0, you're saying there's no chance I've made an error, and there always can be when you're using a sample to estimate your data. So that's our statistical conclusion. We're rejecting the null because our obtained P of less than 0.001 is less than the critical P of 0.05. Substantively, this is our conclusion. There is evidence to suggest that grade in school, that's our independent variable, so whatever your independent variable is, you put in there, that grade in school affects scores on a math test. That's your dependent variable. And that's what goes there. F with 2 and 6 degrees of freedom is 380.33. P is less than 0.001. Okay. One more pattern of scores. Again, we've got all first graders here, and we're looking at how type of studying affects math test scores. So studying alone, studying with a friend, or studying with the TV on. Okay, we've got the 3 people studying alone. Their mean score was 14. Studying with a friend, their mean score is 16.33. But studying with the TV on, their mean score was 6. It looks like I'm trying to send a message here about how is best to study or how is best to not study. Again, made up scores, but let's go through. Step 1, state the hypotheses. Hypotheses are always the same in ANOVA. The null is that mu1 is equal to mu2 is equal to mu3. The alternative is that the null hypothesis is not true. We'll run our statistical analysis in SPSS, and here are our means. Going into ANOVA, we have the same degrees of freedom, 2 and 6. Here's our mean square for between, 88.11. Mean square within, 6.78. Divide those would get you this F ratio of 13 and our significance of 0.007. So we need to compare 0.007 to 0.05, and 0.007 is less than 0.05. So statistically, we will reject the null because our obtained P of 0.007 is less than the critical P of 0.05. Substantively, there is evidence to suggest that type of studying alone, studying with friends, studying with the TV on, affects score on a math test. F with 2 and 6 degrees of freedom is 13. P is equal to 0.007. All right, we've gone through those steps in 3 different problems, and I hope those are making sense to you. But that's not all with ANOVA. We've got one final step, something called post-hoc testing. When an ANOVA gives you a significant result, like we did for the last 2 problems, for grade in school, we had a significant ANOVA, and type of studying, we had a significant ANOVA. It tells us that at least one group differs from all the other groups, but the overall ANOVA does not tell us which groups are different. So in order to know which groups, which specific means are different from which other means, we have to do what we call a post-hoc, after the fact, testing. And there are many, many types of post-hoc testing. Most common ones look at 2 means at a time. We call those pairwise comparisons. And that's for us, we're going to look at just one type of post-hoc test. So it goes beyond your significant F ratio, so that first F ratio that we did. If you have a significant F ratio, it does not mean that all the possible means were different from each other. It just means that at least one group mean is different from at least one other group mean. So if you think about the possible comparisons for the grade in school, we could compare the 1st to the 5th graders, the 5th graders to the 12th graders, and the 1st graders to the 12th graders. Those are the 3 possible comparisons for those groups. And post-hoc testing will let us look at all possible comparisons to see which means were really statistically significantly different. We're going to use the test called the Fisher's Least Significant Difference Test, LSD is how it's abbreviated, which is basically doing a bunch of modified individual t-tests. Remember that this is called post-hoc testing. Post means after the event. And in this case, the event is our overall test, our overall ANOVA. You have to first do our initial ANOVA, which caps your type 1 error rate at 0.05. And if that is statistically significant, then you go on to do your post-hoc testing, and that keeps our type 1 error rate capped at that 0.05. So back to the example of the 3 different schools. Okay, we had school A, school B, school C, and we said that this was not statistically significant, no effect on math test depending on which school. You can ignore this R squared, we're not covering it in here, that would be effect size, but don't worry about it, we're just focusing here. Not statistically significant. Do we do a post-hoc test? And why? Well, we don't, because you have a non-significant overall F test, you don't go on to do anything post-hoc. Because what we're saying here is that there is no statistically significant difference, that's what this is telling us, where there's no statistically significant effect of school on math test score. And because there is no effect, there's no need to go forward to say, well, which means are different from each other. If you did do the post-hoc test, everything would be not significant. Because we're saying there is no difference between what school you go to and your math test score. So if you have a non-statistically significant ANOVA, you don't do a post-hoc test. Yay, and you're very happy. Let's do the next one. Here we are at grade in school. 1st grade, 5th grade, 12th grade. This was statistically significant. We said, yep, there is an effect of grade in school on math test score. We go on and run the post-hoc test, which I'll show you how to do in our SPSS lecture, but this is what they look like. What this does is compare each possible group. So it's comparing our 1st graders to our 5th graders. The mean difference, this is negative 40. It's telling you that when you subtract the mean score, this was a 14, I think, for first graders, and a 54 was the mean for fifth graders. 14 minus 54, that's negative 40 points. First graders scored 40 points less than fifth graders. And then you just go to the significance column. This has to be less than 0.05, and in fact it is. It's saying that's a statistically significant difference. First graders scored significantly lower than fifth graders on math. Here's the next comparison. First graders compared to 12th graders. Just do it sort of this diagonal here. First grade compared to fifth grade. There was a 78-point difference. And again, that's statistically significant. Yes, we have a statistically significant difference between first graders and 12th graders in math. Now you've got to look and find which is your last comparison. We've compared first to fifth, we've compared first to 12th, but now we've got to compare fifth to 12th graders. Fifth to 12th graders, you see it's the second line. That's a 38-point difference, and again, that's statistically significant. So you know that all three of our comparisons are statistically significant. We have, and I'll show you how to write that up here. So first versus fifth grade, statistically you reject the null because our obtained P of less than 0.01, right, is right here, less than 0.01, is less than the critical P of 0.05. Substantively, first graders scored significantly lower, which their mean and standard deviation, that was from our descriptive statistics, 14 and 2. It all comes out, here it is, 14 and 2 for the mean and standard deviation. Then fifth graders, who had a mean of 54 and a standard deviation of 4.36 on the math test. First compared to 12, again, we reject the null because our obtained P of less than 0.001 is less than the critical P of 0.05. First graders scored significantly lower. Again, there's their mean and standard deviation. Then 12th graders, who have a mean of 92 and a standard deviation of 3.61 on the math test. And then lastly, fifth graders compared to 12th graders. Statistically, again, we reject the null because our obtained P of less than 0.001 is less than the critical P of 0.05. Substantively, fifth graders with a mean math score of 54, standard deviation of 4.36, scored significantly lower than 12th graders, mean of 92, standard deviation of 3.61 on the math test. Coming back to this, I do want you to see that even though we have 3 possible comparisons, there are actually 6 lines, or 6 comparisons. This is because SPSS is a computer, and it does things sometimes redundantly, just because it can. So for example, here it's comparing first graders to fifth graders, and first graders scored 40 points less than the fifth graders. But if you come down to the second major kind of box here, now it's comparing fifth graders to first graders. And they're saying fifth graders scored 40 points higher than the fifth graders. Everything will be the same. Standard error, significance, all of your numbers will be the same. It's just that this one will be negative and one will be positive. But it's what we call a redundant comparison. There are only 3 unique comparisons here. First to fifth grade, first to 12th grade, fifth to 12th grade. And you don't want to then go ahead and compare everything again, just the opposite way. Fifth to first, 12th to first, and 12th to fifth. You only do the 3 unique comparisons. All right, last one. This was all first graders types of studying. And again, we had a statistically significant result. Studying alone, their mean was 14 on the math test. Studying with a friend, the mean was 16.33. And studying with the TV on, oh no, their mean was a 6. Okay? Again, ignore the degrees of freedom, or the effect size down here. And we have statistically significant results, so we have to interpret our post-hoc tests. So here we go. Studying alone compared to studying with a friend. Is that statistically significant? Is this less than 0.05? It's not. So there's no difference studying alone compared to studying with a friend. There's just about a 2-point difference. Studying alone compared to studying with the TV on, here's an 8-point difference. And that is statistically significant because 0.009 is less than 0.05. And again, we've looked at studying alone compared to studying with a friend. Studying alone compared to studying with the TV on, and now we need study with a friend compared to study with the TV on. That's a 10-point difference, and again, that is less than 0.05. 0.003 is less than 0.05, so that's statistically significant. So here we go. Studying alone versus studying with a friend. In that case, we fail to reject the null or accept the null because our obtained P of 0.314 is greater than the critical P of 0.05. Substantively, there is no significant difference in math test scores for first graders studying alone. Here's their mean and standard deviation compared to studying with a friend. And again, you write the mean and standard deviation. What about studying alone versus studying with the TV on? Okay, statistically, we're going to reject the null because our obtained P of 0.009, that's right here, is less than the critical P of 0.05. First graders who study alone scored higher on the math test, 14, with a standard deviation of 2, compared to those studying with the TV on, with a mean of 6 and a standard deviation of 2. And lastly, studying with a friend versus studying with the TV on. Again, we reject the null because our obtained P of 0.003, which is right here, is less than the critical P of 0.05. First graders who study with a friend scored significantly higher on the math test with a mean of 16.33, standard deviation of 3.51, than those studying with the TV on. Mean of 6, standard deviation of 2. So what this is telling us is studying alone versus the TV, studying alone is better. Studying with a friend versus studying with the TV, studying with a friend is better. And studying alone versus studying with a friend doesn't matter. You're going to do just fine either way. So what's the big problem here in terms of studying? Studying with the TV on. That seems to be the one that impacts scores in a negative way. Okay, I hope that made some sense. If you need to go back and review some of this, please do, and then our next lecture will be just how to run this in SPSS. Thank you.